Okay, so we've got another example here of a linear first order ODE. And this one might be quite familiar to electrical engineers, where I represents current and T represents time. We note, however, that this isn't quite in the following form. Right, that's our canonical form. And we've got this 4 floating around, kind of messing things up a little bit. But 4 is 4, so we can just divide through by it. Oops, not an equal sign, plus 3i equals 15. We do also have this initial condition that's unchanged by this division, obviously, but this is the ODE now in canonical form, and we can associate 3, a constant function of time, and 15, also a constant function of time, with P and Q. That means we can calculate the integrating factor, e to the integral of 3 dt. Now remember, we don't need a constant of integration here. That's our integrating factor. Multiply throughout by our integrating factor. And use the magic of the integrating factor to collapse this right-hand side. Remember, that's the entire reason that this integrating factor exists, is so we can do this step. But what that does is it gives us a total derivative on the left-hand side. So this now can be solved by integrating both sides with respect to t, which we will do. Integral of e to the 3t is e to the 3t divided by 3. And we remember that we now need a constant of integration. This expression is trivially invertible for I. And we have our general solution. We were given an initial condition. We were told that I of 0 is equal to 0. And that should be enough to solve for C. We simply plug in the values. 0 equals 5 plus C e to the minus 3 times 0 . 5 plus C equals 0, because e to the 0 is 1. And we find that C is equal to minus 5. So our particular solution is I equals 5 minus 5 e to the minus 3t. Okay, we're done.